Okay, so from the lesson, you learned all about waves, so the speed of waves. You also learned about what happens when waves transfer from one material to another material. So you learned about some of the energy transmits through and some of it's reflected off the boundary. And so now what we're going to look at is a consolidation of this and a little consolidation lesson. So waves at boundaries. So from our investigation, we observed a few things about mechanical waves so far. Mechanical waves require a material to travel through. Remember that? So they require a material medium. They travel at a constant speed in a uniform medium. So depending on what the materials are, the makeup, the tension, whatever the case is for that particular material, waves, no matter how big or what wavelength or anything that they're at, they all travel at the same speed. The speed of the wave depends on the type of material or medium it is traveling in or the tension of the medium. The speed does not depend on the size or amplitude of the wave. So those are some key points, right? So you're definitely going to want to make sure that you understand those three key points. And again, that was all explained in the last tutorial. Okay, now, so what did you learn about? Well, wave reflection. So if you have a solid boundary and a wave comes in and it's moving at a particular speed in this direction, we know that when it hits this boundary, it reflects back, but it reflects back with the same amplitude on the opposite side. So it inverts. Okay, that's if it hits a solid boundary. The wave will invert and move backwards. So we learned that. Now, if this was an open-ended situation where this was maybe on a loop, the loop would go up and then it would reflect back on the same side. And we learned that in the video tutorials and you saw those demonstrations. Then what we learned about was what happens when waves interact with one another. And so what we did is, now in class, we would have had two slinkies set up and there's a boundary right there. So there's the boundary. And we have one wave that goes in this direction at this speed and one wave that goes at this direction at the same speed. Remember, they have to be at the same speed because they're in the same material. Now, what you learned and what you found out from yesterday in the videos was that after interference, we learned that the waves, don't bounce off of each other. So some people think they bounce off, but that's not true. What happens is the waves pass right through each other. Okay, so waves pass through. Remember, particles don't do this. Particles would bounce off of each other. Waves can pass through each other. Remember, it's the energy. The particles themselves in transverse waves are only going up and down. There's no material moving. The only thing that's moving is the energy. Now, during the interference, you'll see that this part is bigger than this part. So in this case, during the interference, right in the middle when they meet, you're just going to have a little bump like that. Okay? And you'll see that if you remember, if you knew how many units this was and how many units this was, the difference between the two of them, because one's positive and one's negative, tells you how big this little bump or superposition will be. So remember that the word we used was superposition. And all superposition says is add up the waves, either positive or negative, and the result is what the wave will look like during that point in time when they're interacting. Okay. This type of interference, because we ended up with a smaller wave, is called destructive interference. Destructive interference. Okay, let's check the next one. All right, so the next one, we've got the same investigation, but we're going to put, I don't know why it's grayed out like that, and we're going to put the two crests moving towards each other at a very particular speed. You can see there. After interference, I'm going to try and keep the relative sizes the same as that picture. Right? The wave simply pass through one another. Waves pass through one another. And then the principle of superposition takes place during the interference. And if we look at the point where these two waves meet, you've got this much of a positive crest, this much of a positive crest. They add together to give you a large amplitude crest, just for that brief instant where they're meeting. What did we call this? This was constructive interference. Now, we talked before about noise canceling headphones and things like that. So noise canceling headphones are situations of destructive interference where you play back a sound to your speaker that's the opposite or it's inverted to the sounds outside of the speaker. And what it does is it nullifies it and it cancels it right out. So all you hear is the actual music that you want to hear. There's lots of applications of this. They use destructive interference in airplanes and in helicopters to reduce vibrations by playing feedback that's opposite or it's inverted to the other sounds. So it's pretty cool. You can do a lot of research on that and learn about it. Anyways, constructive and destructive interference of waves is super, super important. When you get into quantum physics and all those sorts of things later on in university or even in the grade 12 course, you are going to see how important this is for light, for waves, for just understanding the fundamental natures of the universe. And you'll see how, even particles can behave like waves and undergo these types of interference. All right, what happens if a wave passes from one material to another? All right, so this is another consolidation. And you can see here, so from a light slinky, we call that a fast slinky, to a heavy slinky, which we call a slow slinky or slow spring. Okay, and this is from slow to fast. Okay, so here, the wave's coming in pretty fast at a high amplitude. If it hits a solid boundary, then the wave will transmit through at a smaller amplitude on the same side and be traveling slower. And the wave that reflects back will reflect back a little bit smaller, but at the same speed that it originally came in. So this is called the transmitted wave.
Dada, look at my small name.
Oh, that's very good, sweetheart. Okay. Transmitted wave. And here is the reflected wave. Okay. Now the transmitted wave transmits through slower with a smaller amplitude, and the reflected wave transmits back at the same speed as the original wave and a little bit smaller. The two energies will add up to the original energy if there's no loss due to friction, sound, all that kind of stuff. All right, in the second part, we've got a slow material into a fast material. Well, in the fast material, you're going to end up with a big, fast wave. And because you're hitting a less dense or a fast material, the reflection is like hitting an open boundary. It's going to reflect back on the same side. Now its amplitude will be smaller, maybe not quite this small, but in any case, but it will be moving at the same speed it was originally moving, but on the same side. So the transmitted wave is always on the same side as it comes in. And if it hits a hard boundary, it reflects back on the opposite side, or if it hits a soft boundary, like this. Now, this happens with everything. This happens with light. It happens with sound. It happens with any wave that exists in the universe. This will happen if waves travel from one material into another. And we talked about it before where particles don't do this. Like if you look at a window, if you throw a marble at a window without breaking it, the marble will bounce back completely. Whereas if you shine light at a window, some of the light will transmit through, some of the light will reflect. The transmitted wave is called the refracted part, and the reflected wave is just the reflected part. And so that occurs there. This occurs, if you were in a room and it was really, really cold in this room and really, really hot in this room, and there was an opening and you yelled at it, you would actually get a reflection off the surface where the two rooms meet. Most of the energy will transmit through, but some will reflect back off that boundary, a very small amount. Now, remember that we talked about in the other video that if the two substances here, the two materials are very, 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 very different, like this is super, super heavy and this is super, super light, almost all of the energy just reflects back and very little goes through. If the two materials are if the two materials are extremely close to being the same, almost all of the energy just transmits through. You wouldn't even notice any reflection. The reflection would just be a tiny little bump. And then the other side would just have a big hump, very similar to, or big crest, just very similar to what it was before. So the amount of reflection and transmission really depends on what the two materials are made of. Okay, so that's it for the consolidation lesson and my daughter's cameo appearance.